Good morning, good afternoon, good evening for all those who have registered to the webinar on using AI ML for network-optimized DDoS mitigation. This webinar is organized with Nokia, and this is the first of many, I believe, that APAN will be organizing. So a bit on the speaker, Jérôme Meyer. He drives the DDoS security research and competence development at Nokia as part of its Deepfield portfolio of network security and analytics. Based out of Paris, he joined the company's mobile networks organization in 2005 in Malaysia, and he's since covered a variety of sales and pre-sales responsibilities in the Asia-Pacific region before returning to Europe in 2023. So not take much time. Jérôme, over to you. If you have questions, we have the Q&A enabled, so you can drop in your questions there as we go. And Jérôme, are you able to see the Q&A?
Yes, I am.
Okay, all right, fantastic.
Yep.
Over to you then.
All right. Thanks, Kiana, and thanks everyone for having me today. So for today, what I have for you is a quick presentation to first talk about briefly the state of DDoS. So DDoS, distributed denial of service, is something that has been evolving despite the appearances for the past couple of years, even though it's been around for more than 2 decades. And then I'll cover some of the different types of DDoS attacks and how this is requiring different types of responses in networks, and particularly in medium to large scale networks, including NRANs, as we have been starting to cover in the past couple of years. And then finally, I will close it with how we can apply some machine learning techniques with the network infrastructure, and talk a little bit about how we are doing this with our Deepfield Defender portfolio at Nokia. If you have any questions, as Liana mentioned, don't hesitate to ask in the Q&A panels. I will do my best to respond as we go, and hope to make this an interactive session. So maybe first, so to look briefly at the state of DDoS for the first 2 decades, roughly, of the existence of DDoS. The common wisdom really had been to look at traffic coming from outside of the network, coming into your network. And that was really the model, so the kind of castle and moat model that has been around for security for the early part of the security domain. So to monitor what's coming into through peering, through transit links into the network. That has worked for some time, but now for the past, let's say 4 to 5 years, we've seen different types of DDoS threats come in. And particularly with the development of IoT and the rollout of IoT devices throughout consumer homes in particular. So as you can see here, a lot of subscribers, myself included, love IoT devices. We have plenty of those in our home networks. And it turns out that a lot of those devices either don't get updated for security issues very often, or more often than not at all. And the other thing that these IoT devices do is that they now, in a lot of places around the world, have access to those gigabit uplink fiber home connections, which means that they can also, when they are compromised, send a lot of malicious traffic to unwitting targets. So this has really become, for the past, let's say now 4 years, roughly, a big component of the sources of DDoS traffic, with those devices being compromised as part of botnets. So there are many types of botnets, but we see a lot of activity, particularly for DDoS driven from those botnets. What's even newer, and this is something we've started to see really come in since last year, is in addition to botnet and more traditional sources of DDoS, is proxy-based DDoS. And for that one, that will be quite different because we've seen this driven by people loving, besides their IoT devices, also loving free VPNs for the, let's say, appearance of privacy that they provide for most of them. What those really do for a lot of those free services is that they have to monetize their service somehow. And if they don't get the money from the subscribers that use them, they will get money from attackers that can then access those devices to get a clean IP address to reflect and to relay traffic from. Those proxies are not just used for DDoS, of course. Originally, so they have been a lot of use for for sending spam emails, for some fraud. More recently also, and that's been quite interesting to observe, a lot of those proxy services have been marketing their ability to scrape websites, in particular in the age of Gen AI training. So when OpenAI and other AI companies have to learn from the open internet, so they crawl different websites, and those proxy services can afford some level of anonymity so that those services cannot be blocked by the websites that they visit. So this has been a thing for several years, but particularly in the case of DDoS, we've seen a lot of increase for proxy-based DDoS traffic, particularly for layer 7, so the application layer DDoS traffic. So I'll get into a bit more of that in the second part of the presentation. So before I get to some more concrete examples, maybe we can do this in the chat for those who can respond. But does anyone know what do most DDoS solutions today? How do they detect DDoS attacks? So does anybody have any knowledge or experience of hunch of how that might work? So maybe either in the chat or you can respond here, and otherwise I'll get onto the next slide. All right, so I see traffic flow, detect using signatures. And indeed, so this is part of it. What really has been quite a staple of DDoS detection is that traditional DDoS solution really rely on traditionally, so a lot of net flow data, for example. So I think we've seen that come in into the chat. But to detect, a lot of the traditional solutions rely on thresholds. So to look at what amount of particular protocols, or for example, TCP flags, you see in what is the particular, the ratios and the thresholds that you see for your particular network. And this is something that is, if you talk to anyone who has been operating a DDoS protection platform for the past 20 years, this is super painful because you need to define first what are the relevant threshold for your network, and even for your network for the different subparts of your network. So for example, you will have different thresholds for a web server that you are protecting compared to, for example, some IP addresses from a lab, or some IP addresses also from a DNS server. So the threshold is something that is painful to first set up. And also, and I've heard many of our customers say that from traditional solutions, it does require ongoing maintenance to keep up to date, because networks and the traffic that flows within those networks, this is not static, right? So this is something that evolves over time. We see big changes of the way that traffic can shift depending on what applications is more popular. So threshold-based detection has worked for some time, but now we believe that it is something that can be replaced by something that can be more automated, and this is where the machine learning part comes in. So I will explain a little bit more what I mean by that in the next few slides. And maybe to get us started, so I don't know how many of you have actually dealt with DDoS. So for those of you who are a bit familiar, so please bear with me. But I will start talking about the most, so the original type of DDoS, which is really amplification. It is something that's been around for more than 2 decades, we still see it today. So it is still a big part of DDoS, and I will explain why that is. So what I'm showing here is actually something coming from our internal platform, which is that, so we are basically looking up an IP address, and we are, so what we are doing is to get some information on that IP address. If some of you have used, for example, Census or Shodan, this type of services, so this is quite similar. And this is something that we build in our own infrastructure at Nokia to get information, so to understand what type of device, what type of services is running on different IP addresses and where they come from. In this case, what we see here on this IP address that is in a Vietnamese service provider, we actually have different types of labels. So this is something that I will come back to, and when we talk about machine learning and learning and training models. So the label data will be important. And what we have here in particular is we have this DNS all tag. So this is something that we build by looking at all of those IPs, which service they respond to, so which request they respond to. And in this particular case, we label it as all because it is a DNS server. But it is not just any, let's say, a vanilla DNS server. It is something that responds to the any type query, which means essentially asking this DNS server to provide all the different record types between A, quad A, and all types of DNS records from a particular domain. And just to give you a bit of a sense of what type of response that can provide on the next, so on this one, and then that may be a bit small, but you get the gist, is that if you, for example, do this any query for nasa.gov to this particular IP address in Vietnam, you will get for a very small query. So the query, I think, is just tens of bytes. You will see a response that is more than almost 4 kilobytes, right? So this is something where you can have a very small initial packet, and then you get multiple packets in response that will go, of course, to the victim, to the target of the DDoS attack. So this is really the basic mechanism of amplification-based DDoS. What we, of course, see here, so this is just another way to look at it in Wireshark, where we see, so in the first line will be the response that I sent over to this particular DNS server, so the DNS resolver here. So yeah, 79 bytes of the wire with Ethernet frame. And then we have 3 packets in response. So what the attackers will do is that they will send packets, so they will send those DNS requests packets from networks or from autonomous systems that will allow for spoofing IP addresses. And instead of putting their own IP address, they will put the source IP address being the one of the target they want to hit with amplification-based DDoS. So this is, at a quick glance, just to explain a little bit how reflection amplification DDoS works and still works very effectively today in generating a lot of traffic based on a very small amount, relatively speaking, of initial traffic. So again, just a bit more details on that. So this works because it is based on UDP. So typically, since for UDP, so there is no handshake, it is easy for attackers to spoof the IP address in networks that don't filter on spoofing. The amplification factor for this particular request is 59 times. So meaning that if we compare the initial request with the response that the DNS server sends, so we are increasing by roughly almost 60 times the initial traffic that is incoming, which is a big reason why we see these types of amplification-based DDoS being a large part of the total amount of bytes that flows into networks, and in particular when we look at the aggregate of DDoS attacks in different types of networks. Okay. So like I was mentioning, so really DNS amplification is not new. It's been around for almost as long as DNS as protocol has existed. It is still something that we see, I mean, that I see in almost every attack. So this is something that is really, really super popular even today. It is something that you can launch for free. So if you go into some commercial DDoS stressors or booters, so essentially those sites that allow people to launch DDoS attacks from their infrastructure, which of course in most jurisdictions is illegal. This is something that is easy to do, but can have a big impact, especially to generate a lot of traffic that can easily congest so the transmission links. So especially relevant for mid to let's say small scale of networks that have, if you have a couple of gigs, a couple of tens of gigs of peering capacity, that can be something that can be quite damaging, because even if you can block it at your network edge, your internet connectivity will still be disrupted. Okay. And so what we see really is that this is typically used nowadays as a complement to more sophisticated, more modern types of attack vectors, so that it can first fill the pipes, and then there can be other attack vectors that can have different impacts. And I will get into those in the next few slides. So how do we detect even this basic type of DNS amplification? So the way that we detect it, and I will explain a bit how we do it, but we can see in the case of in our product, so in Deepfield Defender, which this is a screenshot of here, we see we have the different detection rules. So here, no thresholds. So this is purely the result of the machine learning based detection techniques. I will explain a bit how those work by taking an example. For example, so for one of those detection rules, which will be I believe, so this is the DNS port combo detection rule. So what we do is that we use this language. So it's called the Deepfield model language. So if any of you are familiar or have worked with Python and pandas data frames, so this is quite similar to it. This kind of based on it. And what we see is we use different attributes to describe signatures of the traffic. So this is also goes back to one of the responses in the chat a bit earlier, where we try to describe what malicious traffic can look like. And in this case, it's a pretty straightforward one. So we are just looking essentially at some of the attributes that are included in a lot of the NetFlow records. So this is the protocol that a lot of routers can use to export statistics of what the traffic is flowing through those routers. And typically those NetFlow records will at least include 5-tuple information. So with a destination source addresses, port, protocol, and a few other additional attributes. In this case, so this is, so we can see we are filtering on protocol 17, so which is UDP, source port 53 for DNS. So here we're looking at what is DNS, DNS responses that is coming into the network. And additionally, we are looking at the destination port that is in a list of different known ports, because we would expect that for most DNS responses, those will be not going to those ports. So this is something that would be extremely unusual. Typically, those responses will be going to ephemeral ports. So in this case, we are describing a very specific rule to highlight those unexpected port combination between the source port and the destination port for DNS responses. So I see that there is a question on whether there are any free tools for checking DDoS attacks. So I know that I think that there are some open source tools that exist. And for example, I'm thinking of, so I've been discussing also with your colleagues in Géant in Europe, where DFN CERT, so in Germany has developed a tool for this type of DDoS analysis, which is called NEMO. So this is something that exists as a free and open source tool. But of course, I think what we'll see in the next slide also is that the capabilities are quite different, and where the difference that will exist between NEMO, for instance, and what we can do with additional internet context with Deepfield will be, so I will talk about this in the next slides. Okay. So, which actually brings me to this one. So in this case, we are upping the level of difficulty a little bit here, and you can see that the diff, so the expression, so the signature that we have in this particular detection rule is a little bit more complex, where we have not just addresses and protocols and ports, but also we have this attribute called genome source. So genome is what I was showing a little bit earlier. So it's basically the security map of the internet, where we collect information. So we seek information on the different services and applications and software that the different IP addresses are running. And this is what we can use to enrich the flow data that is coming from the routers. And in this case, we'll use that to refine the detection rules, so what we'll use to classify the traffic, and in particular to have this subtype of DNS amplification. And in this case, we'll focus on the fragments that are coming from DNS servers. Because when we see typically IP fragments in networks, so this is nowadays pretty unusual. It's still valid, right? But it is, in legitimate traffic, this is very unusual nowadays. And what we are trying to do here is to see, when we see fragments, can we actually attribute it? Is it really a legitimate fragment, or is it fragment coming from known DNS amplifier? So in this case, we can see, if we look a bit more into the expression, we'll see that we look still at protocol 17, so UDP again, to indicate, so to look at just UDP, so fragments based on UDP. With port 0, so this is again an expression that this is for fragments which will have no ports. And then we look, what's the more interesting part? We look at the source information on the source IPs, so the source addresses, see if we know them as known DNS amplifiers. So this is what we have in the third component of the expression here. And we will also, because we can have valid fragments in the case of some DNS traffic, and particularly from some public DNS resolvers, from some name servers, whether at root level or at ccTLD level, or some known name servers. So we are actually adding some exceptions for those types of legitimate use of DNS fragments. And this is what we'll express here, which means that we can really have a very granular attribution of the fragmented traffic if we know that it is coming from known amplifiers, while excluding some legitimate use of fragments for some name servers that we know can typically also generate some large responses. So this is just taking it a little bit of a level up. So as we just saw, so there are benefits, and again, this goes back to the question earlier about so whether there are free tools. So yes, there are. Most free tools will really rely on the 5-tuple information from the flow information. So basically looking at how many IP addresses are sending traffic, what protocol, what ports. What we can add here, and what is relevant in the context of machine learning, is that we can enrich this flow information with information that we are collecting and crawling continuously on the Nokia side to have better and more accurate outcomes. Because when we see a lot of DNS responses, we can see this is launch DNS responses coming from the root servers, which is something that you shouldn't block, right? Or we should be very careful in blocking root DNS traffic, versus DNS fragments coming from known DNS amplifiers, which there are hundreds of thousands. So this is information that can be that is very relevant to make sure that we reduce the false positive rate. So to make sure that we don't accidentally block legitimate traffic because we think it looks like DDoS. And also at the same time, being more accurate in reducing the false negative rate. So what amount of DDoS are we actually missing because it doesn't fit into those basic signatures? Okay. One very important thing also I should note is that with those types of signatures, which is part of the machine learning models that we use, and we have hundreds of those signatures. So this was just to show a few of those examples. But it does provide some explainability because we don't want, and especially when we talk about mitigating DDoS traffic and potentially dropping traffic in a network, we don't want just for this to be a black box. So it's very important that when we talk about machine learning being applied to policing and dropping traffic on a network, it has to be explainable. So this is really why also we spent, we use that in a way that can be explained by having those models that can be parsed and that can be we can then backtrace when we have a mitigation. So this is something that is very important for us and for this approach to mitigate DDoS. Just a quick one. So before I move on to the next type of attack type, so I talked about genome, and maybe just to elaborate a little bit because I was a bit quick on that one. So what we include in genome, so the security map of the internet that we are building on the Nokia side. So we have, of course, some general domain knowledge. For example, I mentioned the DNS root servers. So those are public, IP addresses that are published by by ICANN. So this is something that is public knowledge. We are also, so maybe let me use the pointer here. So we are also using, so we are also crawling the internet. So just like Google and OpenAI and other companies that are systematically crawling the internet to see what's out there. So we do crawl the global IP address space to understand what type of services are provided for each IP address, which UDP-based services are deployed, which type of CVEs, so the vulnerability indicators are present on different types of devices. And this is particularly relevant when we talk about botnets to understand which device, for example, are there some TP-Link routers that are compromised and that can be then used to send DDoS traffic. So we see a lot of those typically, and we keep track of those in genome. There would be the rule set. So I showed you some of those rules and we keep them. Of course, it is an ongoing effort to keep them updated, to refine them. So this is something that will be also included in genome. And finally, and very importantly, we have a program that we typically invite all of our customers to participate in, which is to share anonymized DDoS attack samples. And this will allow to make sure that we train the data on relevant and real world DDoS traffic. And this is really critical in also the machine learning based approach where you have you can have those models, but we have to train on relevant data. And this is what really is critical to have. So with those real world samples that can be feeding these models. Okay. So a bit more briefly now, I'll talk about botnet-based attacks. So I see a question about which DDoS attacks are more common apart from DNS, and this is perfect timing because this is actually, so botnet attacks are really the most prevalent form of attack vectors nowadays. And when I talked also about the attack samples, so I see there is also a question about what do we mean by attack samples. So I don't mean PCAP, although we do, I mean, we can process PCAPs, but PCAPs tend to be, for DDoS attacks, extremely large and kind of, well, difficult to manage except for smaller or application layer type of attack, so that can be more relevant for that. But what we'll get in terms of attack samples will be an extract from the Deepfield instance that will be with the enriched, so basically more the NetFlow-based records with the address, port, protocol, BPS, PPS, and all those measurements. So that we can then derive statistics and characteristics of the attack. And this is what we see here. So this is actually part of what we have in our internal tooling to represent the attack sample. And in this case, we're looking at an attack sample from a botnet attack. And this is where we see it's quite different from traditional DNS amplification attacks, because we see, so in this case, it's a botnet-based UDP attack. We can see that the packet length is randomized, so it's following a normal distribution curve between 869 to 892 bytes, but following this kind of nice distribution. The ports, whether source port or destination ports, are completely randomized. So there is no, for example, it's not coming from source port 53 like it was for DNS. So there is no common feature between so that we can draw from for this attack. And if we look at TTL, which is also one of the characteristics of the attack sample that our customers send us. So the TTL is also, so there is no one common TTL that is a common feature for the sample. So we see this something that is distributed between the expected range of Unix-based TTL, so something in the, so quite topologically close to the 64 default value for TTL in Linux and Unix systems. So in this case, that makes it quite challenging. So if you just look at purely the NetFlow data, there is not too much that you can do here. Because this, I mean, you don't have really a common feature that you can discriminate against. And this is why we see that the additional information from genome actually helps a lot in this case. So this is still looking at the attack sample, but looking at the IP addresses that are sending the traffic. And what's interesting here is that in addition to the IP addresses that, so I masked here for, and so just for confidentiality, but we have the labels that we have in genome for each of those IP addresses. And it becomes interesting when you can reason in terms of what are the common attributes from this enriched information. Because here, if you look a little bit at it, you can see that there are some common labels. And in particular, you can see that we have a bunch of webcams that are sending traffic, this type of traffic. So we have different labels. You can see between the orange labels and the red labels. So the orange ones will be those we think is suspicious, so potentially malicious. In this case, we can see we have several definitions for webcams that can be abused for sending DDoS because they are not typically well maintained in terms of security patches. And then we have those red labels, which are for known DDoS bots. And by that, I mean, we have seen that IP address in a recent DDoS attack. And by this, so since we label this IP address, and of course we keep it up to date, we can have a pretty good view that all of those IP addresses have actually a common feature, which is that there are IoT devices, that a lot of them have been involved in previous attacks, and that helps us to make a decision about whether or not this is DDoS and how we can mitigate against this specific attack. Okay. So I'll go maybe a bit more briefly on this one in the interest of time. So this is just to pick one of those IP addresses to explain a little bit, how we get that information. In this case, so this is something we do through crawling. So we are systematically, for example, crawling the entire IPv4 address space and all the active v6 space. And in this case, we see that it has it is running OpenSNMP, so it is responding to a standard SNMP poll, and you can see from the SNMP response that it is actually a Ruckus wireless device from 2006. So yes, there are some older devices that are still running with a publicly accessible port on the internet. And this is a lot of that is automated. So I see that there is a question about how we label the traffic. So for the crawling information, so a lot of this is automated. So we have some definitions for different types of devices, and then the crawling happens automatically and is classified automatically. Where there is a little bit more of a manual work is to review the sample to review or not whether those are actually DDoS or not. So there is some supervision here that we do to make sure that we have a high degree of accuracy for the samples that we review, that we include into the training data set. In addition to the SNMP, just to add a little bit about what we get through crawling. So we see that actually it is also, so this particular IP address is responding on TCP port 22, which is for, in this case, SSH. And we can see that it is using Dropbear, so one of the SSH servers out there. And we can see even the version of Dropbear, and we know that this version, and we are tracking those CVs. This version has several vulnerabilities, including some pretty a critical one that can lead to an authenticated remote code execution. So which is something that DDoS botnet operators can use to then compromise the device. All right, so I'll close with the last type of attack before I get into some of the let's say some of the techniques that we use. And this is a proxy-based attack, which is some of the newer type of DDoS that we have seen, and particularly with some geopolitically driven DDoS attacks. So this is something, and I'll mention them here. We've been tracking, and other security vendors as well have been tracking this as one of the many hacktivist groups that is sending DDoS attacks to different entities. In this case, typically, so this is a pro-Russian collective that is attacking various websites in Europe, but also in Asia. So more recently, for example, they have been, and we see that here on the right, this is in the open. So they are stating which websites they are attacking. In this case, we see that in the past week, they have been attacking websites in Taiwan. And this is something, so this is part of a larger collective of DDoS hacktivist group that essentially enroll volunteers to send DDoS traffic from their machines or from VMs that they rent, for example, from cloud providers. But to anonymize the real sources of the traffic, since this is application layer DDoS, typically in this case, this is going to be mostly HTTPS crafted requests that are sent to those websites. They use proxy services. So this is what we, part of the difficulty, because when we talk about those types of HTTPS DDoS attacks through proxies, it is not going to be like DNS and botnet attacks that I talked about before. This is going to be a relatively low number of sources, so in the hundreds, maybe sometimes thousands of sources, very low bandwidth, so low throughput. What we are seeing here, for example, with the screenshot on the right, is it was a few thousands packets per second. So this is something that can easily be missed, at least at the network level. It can fly under the radar. It is, so this is HTTPS, so TLS encrypted, using valid parameters. And yes, the difficulty is that we are tracking botnets, but it is harder to track proxies because those will be more dynamic and they will not always respond to unsolicited requests. So a lot of what the targets do when they are attacked by this type of hacktivist groups that use this type of methods with proxies is that they enforce a geo-block. So they will say, for example, if Malaysia is attacked, then we'll only allow traffic from within Malaysia, which is something that that work to some extent. It depends really on how, first, what is the let's say the typical traffic from that particular customer, but also what is the strategy from the attacker, because there are a lot of proxies that can be sourced from any given country. So this is something that is a bit of a different problem. So in a nutshell, so this is something where so the geo-blocking, in our view, is something that is becoming less and less effective because not only is it blocking legitimate requests from outside the country, from users that can be accessing the website when they're traveling or when they are based in a different country, but also proxies number in the tens of millions. So they are, depending on the provider, the proxy provider that you look at, residential proxies can be bought, and the access to the service can be bought and provide access to tens of millions for the largest ones. So you can easily target. So if you want to attack a particular country, you can easily find thousands of sources within that country, and the geo-block would then be not achieving the desired goal. So this is really also something that we have built into the genome intelligence by collecting data also on those proxy services. So it's a little bit more, so it's a bit of a different method. So we don't crawl for this one. So we don't crawl proxies. We'll rely on some of the services that actually offer that service, so that we can then track which IP address each of those services use. And then we add that information into genome, so that when we can detect on those labels, and then we can mitigate on those labels. And I will explain how we do the mitigation. So I see that there is a question also about for the botnet-based DDoS attacks. Is there a test bed with live botnet to provide the traffic? Well, not exactly. So this is something where there are plenty. So if you look on Telegram, for example, you can look for DDoS as a service type of services that can include botnet to provide attacks. It's of course illegal in most countries, so we don't caution that. What we do instead is that we offer to customers the ability to replay real-world attacks that have been provided by our customers. So of course, they are anonymized, and then we just can modify the destination IP address or addresses of the attack, so that we can have a realistic sample that can be replayed and tested in the customer premises, which is helpful. All right, so last, to close, so I'll talk a little bit about how do we, based on the information we have, what do we do with it, right? So how can we better protect against different types of DDoS with this additional information we have from those machine learning techniques? And maybe just before I get into too much detail, so I think it's helpful to understand also what are the different options that folks have to protect against DDoS. One is going to be that so that there are some services that offer some upstream protection. So for example, if you have a transit provider, they may have a DDoS protection service. This is something that is especially relevant to smaller type of networks. In the middle here, so it's possible to do the on-net DDoS protection. So this would be more for, let's say, mid-size to larger networks. And then in this case, what the traditional solution will be is to have scrubbers. So DDoS scrubbers, which will be appliances that can inspect and then clean the traffic from DDoS. But so this is something that we do. So we have such an appliance, but we think also it's a lot more effective to as much as possible mitigate at the edge of the network. So it's possible to combine those two elements and drop the malicious traffic as much as possible with your existing router infrastructure. This can be done, of course, with FlowSpec. For those of you who are familiar with so BGP FlowSpec, within the capabilities of the routers. So this is something that we also depend on how many filter entries can you install on those routers. And I mentioned both here at the ingress of the network, but now more and more, and maybe this is not yet as much as relevant for NRANs as it is for consumer service provider networks. but we see more and more that it is relevant to filter DDoS before when it enters the network from the subscriber side. Because as we saw, a lot of devices can be compromised. A lot of those webcams are sitting in consumer homes, and it is helpful to stop DDoS, as close to the source as possible. So we have customers that are actually doing DDoS suppression from their subscriber side before it goes to the wider internet and even to their internal infrastructure. But then, of course, so I won't spend too much time here, but there is also inline solutions. So this would be more for smaller type of locations where enterprise type of deployment where you want to have something inline, but of course not something that scales for tens or hundreds of gigabits of traffic. Now, it's a bit of a busy slide. I'll spend a bit of time on that one. So the way that things work, and this is the way it works for Deepfield Defender, but can be extra. It can be something as a general concept. So the way we approach machine learning in the case of DDoS detection and mitigation will be that there will be a part of it that will be running in our own infrastructure. So the learning part that I mentioned before, so the secure genome models and the samples, so the data set that we train on, this will be running in our own infrastructure, right? Because this is quite computationally intensive, as I think most of you know. So it's a little bit similar to how OpenAI will train ChatGPT-4, for example, on their own infrastructure. And then once it's trained, then it provided to the customer for inference. And in our case, the inference will be something that runs in the local customer deployment. So whether it is a service provider network, an NRAN, this can be running in your own network. And the inference is what happens, let's say, in real time, right? So it is getting the information that is coming from the network. So those flow records that I mentioned before. So this is something that is communicated to the Deepfield instance that runs inference on the traffic from the network, applies the models from genome. So this is something that is updated continuously. So there are hourly updates to make sure that this is something that is up to date. And then if a DDoS attack is detected and a decision, or at least a policy has been defined to mitigate it, then Deepfield can then decide on the best mitigation strategy, again, based on the learning, so the training that we have done before, and can push that to the network either with BGP flow spec or netconf, or to the dedicated appliance that can then scrub the traffic. So in a nutshell, so this is really how it works. Supervised learning at this stage in our own infrastructure, providing regular updates on the models, and then inference running locally for the interest of latency and performance, because what we see is that a lot of DDoS attacks are very short-lived. So the time it takes to mitigate the first byte is really becoming more and more important, so that we don't lose time analyzing, diverting traffic. So this is something that happens in real time. So I see that so I see a question. So traffic, it's constantly changing occasionally. 1 week ago can be different from 2 weeks ago. How do you pipeline the traffic sample and send it to the machine learning while updating the model? So I think on this one, we indeed regularly update what are the different baseline and peace time for different types of customers. So this is important indeed, because what the traffic looks like in an NRAN network can be very different from what happens in a hosting provider or service provider. So this is something that we regularly update indeed to make sure that we lower the false positive and the false negative rates. I see another question. So MCE runs on the IP router and the enterprise. Genome runs on Nokia Cloud Infra outside of the enterprise networks. So almost. So the white box here. So this is something that runs in our own infrastructure. So in our cloud infrastructure. And then the mitigation compiler engine, part of Deepfield Defender. So this is something that runs on x86 servers, on standard servers in the network that it is protecting. So it gets the flow data from the routers, and then it pushes the filter policies, so for the mitigation, to the routers as well. but it is running on standard servers. Okay. So to close, yeah, I think I have a few minutes left also for questions. So what we think really a good approach is for DDoS protection. So beyond traditional 5-tuple based type of approach, that the context in which the traffic is analyzed is really matters. So it matters to understand not just which IP address is sending traffic, but what that IP address is, right? So it matters to understand, is it a DNS server? Is it a botnet? Is it an IoT device? Is it a CDN host that is sending traffic? So that we can better distinguish between legitimate traffic and then DDoS traffic and what type of DDoS, right? So this is really becoming especially critical for botnet and proxy-based attacks, which otherwise look like legitimate IP, consumer type of IP addresses that normally fly under the radar. So that helps to detect accurately. So again, the name of the game here is to reduce the amount of false positive and false negatives. So you want to really first not miss DDoS, right? Because botnet attack can be missed unless you spend a lot of time. Even then, it's not perfect when you spend a lot of time adjusting thresholds over time. Really having this type of context helps to reduce that false negative, and also, of course, the false positive, which means that you don't over mitigate, so you don't drop legitimate traffic that should not be dropped because you think there is DDoS happening. Then finally, so I just briefly touched on it, but of course I'd be happy to elaborate, and we can have, I'm sure, some additional sessions on more the hardware side, on the router side. So the hardware that's available in the network also matters. So of course, this is something that can be implemented differently with different router vendors. But and I mentioned it before, but the router capabilities really matter, right? Because there are some routers that can install a lot of, a large amount of ACLs, so the access control list, to block these the attacks at the source. And some others cannot as well. So it really depends on what's in the network, but we really, as much as possible, encourage our customers and networks to really think of this when they are building out the networks, because then you can reuse that investment in protecting the network against those types of volumetric and complex DDoS attacks, right? So I think that's what I had in terms of slides. So I think we have 5 minutes left, and happy to take any additional questions in addition to those I've gotten in the Q&A that I tried to answer on the fly. But yeah, let me know if you have some additional ones or you need some additional clarifications.
If anyone has a question, you can also raise your hand and unmute yourself and ask the question.
All right, so I see, so I see that there is a question from Kunal. So does DDoS affect the line rate of the router? What I can say is that for Nokia routers, no. So this is something that whatever we designed the silicon and the line cards so that there is no impact in terms of forwarding performance to the amount of the filter entry that are installed. So we can, in the case of the latest the 2 latest generation of chipsets in the Nokia routers, for example, we can install up to 256,000 filter entries. And of course, we know that for some specific router vendors, it's not the case. So that's why we have some configurable option to limit the number of filters that are installed so that we don't impact the performance. But of course, that means that will also reduce the effectiveness of the mitigation on those routers. So the more filters you can install, the more granular you can be in the mitigation, and so the more accurate you can be. And so it's always a trade-off between what's available in the infrastructure and what you can do with those routers. And of course, those routers can be used together with dedicated appliances, so they can be a bit of a multi-stage approach where if the routers don't have these capabilities, you can always deploy this appliance that can then be more effective at mitigating this type of DDoS attacks.
We've got two questions on chat from Philip and Serish.
Okay. So maybe I'll address first Sarah's question. So can we develop our own mitigation algorithm using genome dataset? So it is possible. So this is also part of the reason why we made it an explainable model, right? With those those expressions that look a little bit like a pandas data frame. So you can actually develop your own. So if you want to filter on a specific combination of genome information plus port, protocol, address, whatever, you can do that. So we have customers that indeed have have very specific requirements where they want to block or to rate limit specific type of traffic or to allow specific type of traffic, and they can just define that as a DML expression in their deployment. And then, so I see a question on how long do you store the traffic samples of the model? Do you follow any policy for how long do we need to store it? So yes, so in this case, let's say what is important is not so much in terms of retention policy, because we anonymize the samples, so it's really so the customer information is not included in those samples. So which is really about the destination IP addresses under attack. So that one we don't store. What is becoming less relevant over time is really the botnet information. So that's why anyway we edge out the botnet information after a couple of weeks to make sure that we don't use outdated information, because we know the IP addresses will be rotated for a lot of service providers. So it's not we do keep the samples for a bit longer so that we can still benchmark the effectiveness. But then the labels that we create from the samples, then they will be edged out quicker because we want to make sure that we don't over classify botnet, for example, in recent attacks. Right. And then last, I think a question from Philippe. So can you explain what it takes to measure or estimate the level of DDoS in the network? So this is coming from the net flow data that will be coming from the router. So this is completely multi-vendor. So whatever router you have in your network, so they will support some form of net flow, IPFix, S-flow, or whatever. So that can be used to directly export to Deepfield to get that information and to combine with the genome information. And maybe in the context of NRAN, so we do have customer deployments with, for example, in Europe, with Aconet. We have been testing also with NICEF. So if some of you are familiar with NICEF, so the Dutch Institute for Subatomic Physics, who are in charge of testing DDoS solutions for the Dutch government. So this has been tested and validated in the context of NRANs as well. Of course, it will depend on the specific context and requirements of the different NRAN networks. But yeah, happy to, of course, discuss if you have any additional questions. Yeah, are you still there?
Yep, I am.
Yeah, okay.
Did you address Basuki's question on the chat?
Oh yeah, sorry, I didn't see that. Is there any open source for this Nokia Deepfield? So no, at this stage, I mean, for the Deepfield Defender, it's not open source. So this is something that we deploy to customers. But of course, yeah, I'm sure we can discuss and see how what will be the best model for your particular network. But yeah, not open source at this stage. And yeah, on the contact point, so I think on the call, so there will be Philippe and Marilyn. So I think who can be first contact points. So if you need to, if you want to have a follow-up discussion, so don't hesitate. I think Philippe can be in touch to follow up and to see, I mean, to schedule a follow-up discussion.
Okay, then. Exactly an hour from the time we started. So I guess thank you so much, Jerome, and thank you everyone else who's on the call. We would be actually sending out a feedback, and there will be more webinars that APAN will be organizing with our partners. So thank you, Jerome.
Thank you very much. Thanks, everyone.